All right, let's talk about one of those concepts in engineering and physics that shows up everywhere, but always seems a little mysterious. I'm talking about divergence. It looks like some really abstract, complicated math, right? Well, I promise you, by the end of this, you're not just going to understand it, you're going to see it for what it really is. A simple, powerful, and honestly, a pretty intuitive idea.
And this is usually the culprit right here, the del dot operator. I mean, look at it. It's no wonder this thing trips people up. It looks like some secret handshake for mathematicians. But here's the thing. What does it physically mean? Like, what is it actually telling us about a vector field in the real world? Well, that's the big question, and we are going to totally pull back the curtain on this symbol.
Okay, so here's the game plan. We're going to start with that mysterious del dot. Then we'll get into a super simple analogy involving sources, sinks, and sprinklers. From there, we'll cover the rules of divergence, learn about an amazing shortcut called the Divergence Theorem, expose a really common trap you need to watch out for, and then wrap it all up so you never forget it.
All right, first up, the mysterious del dot. We're going to move away from just abstract math and get to the physical meaning. The goal here isn't just to calculate divergence, it's to actually see what it represents.
So, if you crack open a textbook, you'll see something like this. Divergence is the outward flux per unit volume as the volume shrinks about a point. Okay, what does that even mean? Let's break it down. Flux is just a fancy word for flow. Think of it as how much stuff, like water or an electric field, is passing through a surface. So what divergence really is a measure of the net flow out of a teeny tiny microscopic volume right at a specific point. It's basically a number that tells you right at this spot is the field spreading out or coming together.
Now, to make that idea stick, we need an analogy. And for divergence, the absolute best one is thinking about water. Seriously, if you can picture how water flows, you can build a mental model for this that you will never forget.
So, what happens if the divergence is a positive number? Well, that means you found a source. There's more stuff flowing out of that point than flowing in. The perfect picture in your head should be a sprinkler head, just sitting in the middle of a lawn. Water is literally being created or sourced from that one spot and spraying out in all directions. That point has positive divergence.
Okay, so what about the opposite? Negative divergence. You might also hear it called convergence. This is exactly what it sounds like. You've found a sink. More stuff is flowing into a point than is flowing out. The classic example, a bathtub drain. All the water in the tub is heading towards that one spot, and poof, it's gone. It terminates there. That spot has negative divergence.
So, we've got positive for sources, negative for sinks. What about zero? What if the divergence is just zero? Well, it means there's no net source or sink at that point. For any little box you draw, the amount of water flowing in perfectly balances the amount flowing out. Think about a nice, wide, steady river. If you look at any point in the middle, water's just flowing through, right? It's not appearing out of nowhere, and it's not vanishing. It's just passing by. That kind of flow has zero divergence.
Okay, so now that we have this solid intuition about what divergence is, let's check out the math. How do we actually calculate that source or sink strength at any given point?
For our standard x, y, z coordinate system, the formula is actually pretty straightforward. It's just the sum of three simple terms. All you're doing is asking three questions. First, as I move along the x-axis, how much is the x component of my vector changing? Then, as I move along the y-axis, how much is the y component changing? And finally, the same for z. You just add those three rates of change together, and boom, you've got the total spreading outness at that point.
But of course, the world isn't always a neat little box. Sometimes we're dealing with pipes or spheres. For those, we use cylindrical and spherical coordinates. And yeah, I know, these formulas look a lot scarier. But don't let them intimidate you. They are describing the exact same physical thing, that spreading out idea. All those extra terms, like the 1 over rho or 1 over r squared, they're just there to correctly handle the fact that the little volumes we're looking at are curved and change size as you move around. The core concept is identical.
Just two quick but super important properties to keep in mind. First, when you take the divergence of a vector field, you get a scalar field back. That just means your answer at every point is a single number, like 5 or -2, not a new vector with an arrow. It's just the strength of the source or sink. Second, it's distributive, which is just a nice math rule that can make life easier when you're dealing with complicated fields.
Okay, now for the main event. Understanding divergence is one thing, but the divergence theorem? Now that is a total game changer. Honestly, this is one of the most powerful shortcuts in all of vector calculus, and it lets us solve some ridiculously hard problems in a really clever way.
So here's the big idea in a nutshell. The theorem says that if you want to figure out the total net flow, or flux, coming out of some closed shape, like a box or a ball, you actually have two completely different ways to get the exact same answer.
On one hand, you've got the hard way. This means doing a surface integral, which can be a real pain. You have to add up the flow through every single tiny patch on the surface of your shape. Or you can do it the smart way. You can totally ignore the surface and instead just calculate the divergence inside the shape and add up all those little sources and sinks throughout the entire volume. You get to trade a difficult surface integral for a much, much easier volume integral.
Look, talk is cheap. Let's prove it with a real example. We've got this vector field here called G, and our job is to find the total flux flowing out of this sealed cylinder. And to really see the magic, we're going to do it both ways. First up, the hard way. To get the total flux, we'd have to do 3 separate, painful surface integrals. One for the top lid of the can, another for the bottom lid, and a third one for the whole curved side. Then, after all that, you have to add all 3 of those answers together. It's a ton of work, and man, there are so many places you could make a simple mistake.
Now, let's try the smart way with the divergence theorem. It's just 2 steps. Step 1, we calculate the divergence of our vector field, which just gives us a simple number. Step 2, we integrate that number over the volume of the cylinder. That's it. Done. 2 steps.
And what do we get? What's the final answer after all that work? 0. Both methods give us the exact same answer, 0. The total flux is nothing. And what that tells us physically is that for this particular field, everything that flows into the cylinder flows right back out. There are no net sources or sinks trapped inside. The theorem worked like a charm, and wow, did it save us a lot of time. Okay, before you get too excited and start using this everywhere, there is one giant trap. This is the #1 mistake people make with the divergence theorem, so you've got to pay attention to this. Here's the rule. The divergence theorem only works for a surface that is completely, totally, 100% closed. It has to fully enclose a volume. Think of it like a sealed can of soup. The top, bottom, and sides all together make a valid closed surface. But if you take the top and bottom lids off, you're just left with a tube. That's an open surface. The theorem can't work because it doesn't enclose a volume anymore. Your shape has to be sealed shut. No holes, no gaps. That's the one and only rule. All right, let's wrap this all up. Here are the key things I want you to burn into your brain so you never forget them. Okay, 3 things. Number 1, divergence is a physical thing. It's a measure of how strong a source or a sink is at a single point. Just think sprinklers and drains. Number 2, the divergence theorem is your best friend. It's a massive shortcut that lets you swap a nasty surface integral for an easy-peasy volume integral. And number 3, the one big rule. That surface has got to be closed. No gaps, no holes. Sealed shut. So I'll leave you with this to think about. Now that you can actually see a vector field in terms of where it's coming from and where it's going, these sources and sinks, how does that change how you look at other things? Like an electric field blasting out from a point charge, or the flow of air around an airplane wing, or even how heat radiates from something hot. Because you know what? It's the exact same idea. Thanks for tuning in.